In this video, we're going to discuss hypothesis testing regarding the difference between two population proportions. To test hypotheses regarding two population proportions, P1 and P2, use the steps that follow, provided that the samples are independently obtained using simple random sampling or through a completely randomized experiment with two levels of treatment. So there's two things here. We have to have randomness, and the samples have to be independent in order to use this process. Second, N1 times P hat 1 times 1 minus P hat 1 has to be greater than or equal to 10, and N2 times P hat 2 times 1 minus P hat 2 has to be greater than or equal to 10. Again, this requirement is necessary for the distribution of P hat 1 minus P hat 2 to be approximately normal. Third, N1 has to be less than 0.05 times uppercase N1, and N2 has to be less than or equal to 0.05 times uppercase N2. So in other words, both samples have to be less than 5% of their populations. This requirement ensures the independence necessary for a binomial experiment. So really there's two types of independence that we're talking about here. Sample 1 has to be independent from sample 2 in order to use this particular normal distribution to model our scenario. And the other kind of independence is that the individuals within each sample have to be independent from each other. So again, two types of independence. Independence of the individuals within each sample, and then independence between the two samples. So keep that in mind. Two types of independence that we're discussing here. Step 1. Determine the null and alternative hypotheses. The hypotheses can be structured in one of three ways. Now this is similar to what we've done before, but not the same. So our null hypothesis is going to be that the two proportions are equal. So we're going to assume that the two proportions are equal to each other, unless evidence convinces us otherwise. Our alternative hypothesis will then be one of three things. Either that P1 does not equal P2, and if that's the case, then we'll have a two-tailed test. P1 is less than P2. If that's the case, we'll have a left-tailed test. And P1 is greater than P2, and if that's the case, then we'll have a right-tailed test. Step 2. Select a level of significance alpha depending on the seriousness of making a type 1 error. Step 3. We're now going to have two possibilities. We'll have the classical approach and we'll have the p-value approach. Either way, if we're doing this by hand, we're going to calculate the test statistic. So the test statistic is going to be p hat 1 minus p hat 2 divided by the square root of p hat times 1 minus p hat times the square root of 1 over n1 plus 1 over n2. And again, this is approximately the standard deviation of the p hat distribution. That's the significance of that. And p hat in this determination, remember, is x1 plus x2 over n1 plus n2. That is the pooled proportion that we're using to estimate the population proportion. Now again, whether we're using the p-value approach or the classical approach, either one, we're going to calculate that test statistic. Now, if we're using the classical approach, we're going to use the standard normal table to determine the critical values, depending on whether we have a left-tailed, right-tailed, or two-tailed test, and depending on the level of significance. And then step 4, we're going to compare our critical value to the test statistic, or again, I prefer to think of that as the other way around. We're going to compare the test statistic to the critical value. So if our test statistic that we calculate here falls either to the left or to the right of the critical values in a two-tailed test, then we're going to reject the null hypothesis. If it's a left-tailed test and the test statistic falls to the left of our critical value, we'll reject the null hypothesis. If we're doing a right-tailed test, and if the test statistic falls to the right of the critical value, then we're going to reject the null hypothesis. Otherwise, we will not reject the null hypothesis. So that's step 4. And then we'll state our conclusion. Now, By hand, again, if we're using the p-value approach, we'll calculate the test statistic, and then we'll use that to determine the p-value. So if we have a left-tailed test, the p-value will be the area to the left of the test statistic. If we have a right-tailed test, then the p-value will be the area to the right of the test statistic. Now, if we have a two-tailed test, well, either the test statistic's going to be negative or the test statistic's going to be positive. So we're going to use the test statistic and its opposite. So we'll have both a negative and a positive value. The area on the outside of the negative and positive values will be the p-value in a two-tailed test. So like before, if it's a two-tailed test, the p-value will be double what it would be if it was a one-tailed test. Now we could also use technology in order to determine the p-value. And if the p-value is less than alpha, then we'll reject the null hypothesis. After that, we're going to state our conclusion. So this process is essentially the same process that we used previously with hypothesis tests. The main difference is that we have a different way of computing the test statistic because we're dealing with the sampling distribution of p hat 1 minus p hat 2 instead of just dealing with a sampling distribution of a single proportion. So let's take a look at an example. Views on the death penalty. The Pew Research Group conducted a poll in which they asked, are you in favor of or opposed to executing persons as a general policy when the crime was committed while under the age of 18? Of 580 Catholics surveyed, 180 indicated they favored capital punishment. Of 600 seculars, those who do not associate with the religion, surveyed, 238 favored capital punishment. Is there a significant difference in the proportion of individuals in these groups in favor of capital punishment for persons under the age of 18? Use the alpha equals 0.01 level of significance. So what we're looking to do here is to compare the proportion of Catholics who are in favor of capital punishment versus the proportion of seculars who are in favor of capital punishment, again, when the crime was committed by someone under the age of 18. So if I let P1 represent the proportion of Catholics and P2 represent the proportion of seculars, then what we're going to be looking at as a null hypothesis is we're going to assume that the proportion of Catholics equals the proportion of seculars. For our alternative hypothesis, the question is there a significant difference in the proportion of individuals in these groups in favor of capital punishment? So is there a difference is the question. So our alternative hypothesis is going to be that P1 does not equal P2 as opposed to less than or greater than. So this means we're going to have a two-tailed test. Now, for our sample 1, we know that they surveyed 580 Catholics and 180 of them indicated they favored capital punishment. So just summarizing what we know, we'll write that down here. N1 is equal to 580 and X1 was equal to 180. And then for seculars, the sample size was 600 and the number who favored capital punishment was 238. So N2 is equal to 600, which means X2 is equal to 238. So P hat 1 is equal to 180 divided by 580, and P hat 2 is equal to 238 out of 600. Well, if we take 180 divided by 580, that is 0.3103 approximately, so about 31%. And if we take 238 divided by 600, that is about 0.3967, so 0.3967. Now you want to carry this out at least to like 4 or 5 decimal places so that rounding doesn't cause a serious amount of error. Probably even maybe should have carried it out farther than I had here, but we're going to carry it out to 4 places in this particular case. So it looks like there's a difference, right? 31% of Catholics versus almost 40% of seculars. And so the question is that difference significant? Is there a significant difference here? So is this difference enough to say that there's truly a difference between the opinions of Catholics and seculars, or is the difference here perhaps due to variation in samples? Well, in order to use the classical approach, then I need to calculate Z0. So writing down our formula, Z0 is equal to P hat 1 minus P hat 2 divided by the square root of P hat times 1 minus P hat times the square root of 1 over N1 plus 1 over N2. Now P hat here is the pooled proportion, so we're going to have to determine that. So let's do that down here. P hat is going to equal, again, our formula is x1 plus x2 over n1 plus n2, so we're just getting the total number of successes out of the total sample size. So in this case, that is 180 plus 238 out of 580 plus 600. Well, if we do that, 180 plus 238 divided by 580 plus 600, that is 0.3542 approximately. So this is about 0.3542. We're going to use that pooled estimate for this P hat value right here. Now also, in order to be able to do this, remember we have to have independence. So these were sampled individuals, so I will assume that we have randomness. There's nothing stated that indicates that these 580 individuals are related to these 600 individuals, so we'll have independence between the two samples. We also do need to check, is N1 times P1 times 1 minus P1, or really it's P hat 1, is that greater than or equal to 10? And is N2 times P hat 2 times 1 minus P hat 2 greater than or equal to 10? Well, let's just check that really quickly on the calculator. So again, our P hat 1 is 0.3103 and N1 is 580. So if I take 580 times 0.3103 times 1 minus 0.3103, that is equal to 124, which is certainly bigger than 10. So we meet that condition. And if I take 600 times 0.3967 times 1 minus 0.3967, that is 143.597, so we also meet that condition. So we have both types of independence, and we meet this condition. I don't know exactly what the population of Catholics is, but certainly 580 is less than 5%. I don't know what the population of seculars is, but certainly 600 is less than 5% of that population. So we also meet the condition of independence within the samples. So we've met our conditions that are required in order to be able to conduct this hypothesis test. So now let's finish computing the test statistic. So P hat 1, that is 0.3103, minus P hat 2, 0.3967, over the square root of P hat, which is 0.3542, times 1 minus 0.3542, and then that is times the square root of 1 over N1, which is 580, plus 1 over N2, which is 600. So this will give me the test statistic. So if we do this calculation, parenthesis 0.3103 minus 0.3967, close parenthesis, divided by parenthesis. Now I need the square root of 0.3542 times 1 minus 0.3542, and then times the square root of 1 over 580 plus 1 over 600. Close the parenthesis. Now I do have to put the two square roots within parentheses so that the calculator follows the correct order of operations. So that gives me negative 3.102. So this result is negative 3.102. Now, if I'm using the classical approach, then I need to determine my critical values to compare the negative 3.102 to. So we're using a level of significance of 0.01, and we have a two-tailed test. So I'm going to have area in the right tail and in the left tail. Again, we're basing this on a standard normal distribution. So I need to figure out these critical values. Well, the 0.01 is going to be split between the two tails. Half of 0.01 is 0.005. So 0.005 goes in each tail, and we need to figure out what these two critical values are. Well, again, we can do that either by using the standard normal table, or we can use like inverse norm on the calculator, or we can use the normal calculator in StatCrunch. Any one of those will give us these critical values. I'm going to use the calculator. So if I use the inverse norm command, the area in the left tail is 0.005. That is in the left tail. And so I get a critical value of negative 1.598. So this value here is negative 1.598. This value by symmetry is positive 1.598. So our test statistic is negative 3.102, which would fall way over here to the left of negative 1.598. So that does fall into the rejection area, so that tells me to reject the null hypothesis. I am rejecting that the two proportions are equal, and I'm concluding that the two proportions are not equal. So in other words, there is a significant difference in the proportion of individuals in these groups that favor capital punishment for persons under the age of 18. Now, if I use the p-value approach, for the p-value approach, again, I first of all find the test statistic, in this case, negative 3.102. Because this is a two-tailed test, I'm going to find the area to the left of negative 3.102, and I'm also going to find the area to the right of positive 3.102. Again, I'm doing both tails because this is a two-tailed test. So if I find these two areas and add them together, that will be the p-value. So how do I find the area in the two tails? Well, I can use the standard normal table, I can use the normal CDF command on my calculator, or I can use the normal calculator in StatCrunch. Any one of those approaches will work. I'm going to use the normal CDF command on my calculator. So if I find the area to the right of 3.102, then the area to the left of negative 3.102 will be the same, and that will help me determine the p-value. So I go to normal CDF. My lower bound is 3.102. My upper bound is going to be a big positive number. We're dealing with the standard normal, so the mean is 0, the standard deviation is 1. I get 9.61157 e to the negative 4. Now remember, that is scientific notation, so that really means the decimal point is 4 places to the left. So this area here would really be 0.000961 approximately, which means this area is also 0.000961. So if I add those two together, or in other words, if I take this result times 2, that gives me 0.0019 if I round to 4 places. So the p-value is equal to 0.0019. Now, because that is less than alpha, which we're using 0.01, that tells us to reject the null hypothesis. So the question was, is there a significant difference in the proportion of individuals in these groups in favor of capital punishment for persons under the age of 18? And the answer to that question is yes. There is a significant difference. The proportion of Catholics who are in favor of capital punishment differs from the proportion of seculars who are in favor of capital punishment for persons under the age of 18. So there is a significant difference. The results of our samples were statistically significant. In the next video, I'm going to show you this same problem, but we're going to look at how to do it directly on the calculator and in StatCrunch.